Hi, good morning everybody. My name is Catalina Alvarez Covelli, and today I'm going to present spatiotemporal variations of heavy metals in space approach. So mangroves are tropical and subtropical ecosystems that are found in coastal areas. They host high biodiversity, they provide multiple ecosystem services, and among these services, one of them is food supply. They act as nursery and breeding ground of important commercial species. Trace metals are naturally found in mangrove sediment, and among these metals, heavy metals. However, anthropogenic activities has increased the input and relocations of heavy metals in mangrove sediment. Mangrove forests act as a sink and as a source of heavy metals, thanks to the physicochemical characteristics of the sediment as the fine grain size, the high accumulation rate of organic matter, the formation of acid volatile sulfides, low pH, and oxidizing conditions that enhance the retention of heavy metals. With these parameters plus coastal distance, salinity, hydrology, and the biota, they determine the viability and the geochemical fractionation of heavy metals. Heavy metals can be divided in two main groups, according with the role in the metabolism. Heavy metals that are essential and heavy metals that are not essential. In the first group, we found nickel, copper, and zinc, and they normally act as metalloenzymes. They have a specific protein transporter, but high concentration of these metals can be detrimental for the organism. On the other hand, heavy metals that are not essential, as is the case of cadmium and lead, they are considered toxic heavy metals and they go into the cell through accidental transport. So even at low concentration of these not essential heavy metals, they can have negative consequences in the organism. Both essential and not essential are carcinogenic, genotoxic, and neurotoxic and immunotoxic agents. Another important thing is to remember that even at low concentrations in the sediment or in the water, it can be possible that there is still high concentrations in the tissue of the organisms that are above the admissible concentrations for human consumption. And this, it is possible through process of bioaccumulation, biomagnification, and transfers in the food web, that at the end are a food security hazard for the humans. Also, mangroves are normally used in traditional medicine, and that also put a hazard for the humans. So it is essential, the heavy metal assessment for mangrove conservation, and in order to assure the well-being both for organisms that are associated with mangrove and humans. So the aim of this review was an spatiotemporal analysis of heavy metals in mangrove sediment at a global scale from 1988 till present, highlighting the gaps in the methods and indices currently used in the assessment of the heavy metal in mangrove ecosystem. An extensive literature research was done using the research engines and the keywords heavy metal, trace metal, contamination, mangrove, and pollution. The nickel, copper, lead, zinc, and cadmium were the ones that were included in the database because are the heavy metals most reported in mangrove ecosystem. The minimum criteria to include a paper in the database was, first, that it was a peer-reviewed paper, second, that the sampling was specifically done in mangrove areas, and that it provides information about the concentrations of heavy metals in the sediment. Other information that was retrieved from the paper was the location, the sampling year, physicochemical parameters of the sediment, heavy metal extraction method, the grain size analyzed, and the depth. These ones are related with the methods in order to assure the comparability between the studies. A total of 104 papers were included in the general database. However, 14 papers were excluded because they didn't provide the sampling year, which was essential for the temporal analysis. The database was divided in 3 periods, and it was assured for the maps that there was one heavy metal concentration per one geographic coordinate. Instead of using the bulk concentration, it was used so concentrations that were below the threshold effect concentration, TEL or TEC, no adverse effects in the biota are expected, and concentrations that were above the probable effect concentration, adverse effects are expected. As the concentration increases, the probability of finding these adverse effects increases too. Different map layers were also used, besides these of the ecological risk index, for the construction of the maps. So in here we are seeing one of the maps that I made, and in the green regions, the green part are the mangrove coverage. The population density layers, we see that in the darkest areas are the highly dense regions. And in here, the yellow dots are the regions where no adverse effects in the biota are expected. The gray, where there is a low probability of finding these adverse effects in the biota. And the ramp of red, going from the light red or pink to the darkest red, adverse effects in the biota are expected, where the highest probability is in the darkest colors and also correspond to severely polluted environment. I'm going to focus only in nickel and cadmium because they were the heavy metals that was more frequently found at these hazardous concentrations for the biota. So in the case of nickel, what we found is that relative to the total number of records per each period, the percentage increases over time, going from 38% in the first period to 60% in the second and 62% in the third period. And the trend is also observed at a regional level. For example, in the case of the Red Sea and Persian Gulf. The same trend was observed in the case of lead, zinc, and copper. In the case of cadmium, a different trend was observed. And in here, what we saw is that relative to the total number of records per each period, we found that there was a decrease of the records that fall in these categories of hazardous concentrations for the biota, going from 76% in the first period to 53% in the second and 40% in the last period. However, it is important to recall that 40% of the records falling in this hazardous concentration, it is still a big percentage. So another thing that I want to point out is that from the maps, we can show very quickly, but I can go a little bit more later, that there are differences in the sampling among the continents, where 75% of the mangrove surface area are contained in 15 countries, but the top 5 countries, there are few records of heavy metals in the sediment, and in the other cases, in the other countries, there are no records at all of heavy metals in sediment, or at least that fulfill the requirements to be included in this review. The exception is the case of India and Bangladesh, and actually India is just the opposite, being the country with the highest number of publications and records, with 1/3 of the records that belong to India. This could be related with the large extension of mangroves in India, and also with the fact that the Sundarban mangroves, that is the largest in the world, is found in India and Bangladesh. Another thing that I want to point out is that most of the sampling has been done in populated areas and in the proximity to the cities, where is expected an impact of the humans. And this is not surprising, considering that 20% of the world cities that are over 100,000 inhabitants are within 20 kilometers of mangrove ecosystem. So even if there is even if we don't know what is happening in pristine areas that are less impacted. Another thing that I want to make emphasis is in the sources. In the case of nickel, that is the 5th most common element on Earth, sources that are related with anthropogenic enrichment are associated with the hydrocarbon industry, refineries, and the oil combustion. In the case of cadmium, that normally are found in nature at low concentrations and high concentrations are associated with anthropogenic enrichment, they share common sources with nickel, as is electroplating, atmospheric deposition, cultural runoff, domestic sewage, industrial effluents, dredging, aquaculture, both in activities, and cadmium and nickel batteries. The ones that are underland and involved are common sources also for lead, zinc, and copper. But I want to make something clear, and is that we don't know exactly what are the regional background levels. And without knowing these values that are the natural values in mangrove ecosystem, we don't know till what extent the heavy metals that we found in sediment really are from human enrichment and not from natural sources. So one solution will be the use of dated cores. And with that, we could know the heavy metals concentrations in pre-industrial times and also the evolution of heavy metals over time. Another thing is that I want to make emphasis is that in all the regions where we found that were above the probable fact concentration, that means all the red colors, the pink and the darkest and the red, adverse effects in the biota are expected. In the case of nickel, that is essential, and in the case of cadmium, that is a not essential metal, both act as they mimic other cofactors, and both has different effects in the physiology and detrimental effects in the physiology. Also, they cause changes, well, they increase the stress at different levels and in different organisms, and also they cause changes in the behavior. So changes in the physiology plus changes in the behavior can lead to population declines, and that can contribute to a food security problem, taking into account the part where I mentioned that there are important commercial species that use mangrove as nursery and breeding grounds. So now I would like to go with the approach that I use for the maps and some comments about this approach. The threshold effect concentrations and the probable effect both act as ecotoxicological risk index, and they are reference values. They provide more information than only the heavy metal concentration, and they provide information about this risk, ecological risk, and also they allow comparisons not only between the regions, but also in time and between heavy metals. That would not be possible if I only use the heavy metal concentration. Another thing is that there are some caveats related with this approach, and is that TEC and PEC were created for temperate regions, and the observations that they base, the field observation and the experimental observations are being made in organisms of temperate regions, but there is no revalidation for tropical ecosystem, especially for mangrove ecosystem, despite the fact that in the literature, this has been an approach that has been widely used for the assessment of heavy metals in mangrove ecosystem. Another caveat related with this approach is that as reference values, they differ a little bit between freshwater and marine ecosystem, but in mangrove, where there is a high salinity range, the salinity is not considered in these reference values. So as recommendations, I suggest the new, or at least revalidate the current sediment quality guidelines with an emphasis in the ecological risk index, but the observations and the field and experimental observations in mangrove organisms, and also I suggest to integrate viability models that take into account parameters that modify the viability, and use complementary indices that give information about the human enrichment, as is the pollution index or the mean enrichment quotient, that take into account the background levels. And also I suggest to standardize the methods, especially during the sampling, and especially to the parameters that are measured during the sampling. At least it should include pH, salinity, organic matter, and grain size fraction, because they determine the viability of heavy metals in sediment. And also, in terms of the heavy metal extraction, I suggest the sequential one, because that provides information about the geochemical fractionation and therefore the bioavailable part of heavy metals that are in a moment in the sediment. So in conclusion, nickel and cadmium are potential threats to mangrove ecosystem. The temporal patterns are metal specific. There is an special bias in the research that has been concentrated close to urban areas, and there is little information about the heavy metal concentration in sediment, especially in countries with the highest mangrove coverage. TEC and PEC has proven to be a useful screening approach for comparing regions and heavy metals at a global scale, and as recommendations, I suggest the new sediment quality guidelines and ecological risk indices. Regional background levels should be always included, and heavy metal sequential extraction should be the extraction that I would use for the assessment of heavy metals. I want to thank my supervisors, Dr. Martin Simon and Dr. Veronique Helfer, for all the support during my thesis, for the free in thinking and for the liberty in the project. I want to thank the IMBRSea program for the 2 years of the master, and I want to thank my family and friends for all the support during the master and during my thesis. And thank you very much.